high. Renewable energy converters are often benchmarked on cost of energy, and in exercise WT-4 we will compare two turbines, the one installed in the ocean, tidal turbine, and the other one in the river turbine. Actually, the two turbines are totally identical, so what is different is the place of installation. As you know, in the ocean, if we have a tide, it will reverse 4 times a day, while in the river the flow will be constant. To calculate cost of energy, we need much more data than just the load on the propeller. So we need cost information, cost of installation of the turbine, cost of the foundation of the nacelle of the propeller itself, even cost of the research of the place of installation of the turbine, and these costs are actually higher than the cost of the power conversion stage or the drivetrain itself. In this exercise we assume the river turbine is located 500 meters away from the shore, while the tidal turbine, the ocean turbine, is located further away, and there are two variants to consider, two cases. The first case is 1 kilometer away and the second case 3 kilometers away. So this sets the length of the cable between the shore, the grid, and the turbine. So why we consider two cases for the ocean turbine? Because we want to investigate how the solution with the park consisting of maybe 10 or 20 tidal turbines would look like cost-wise and cost of energy-wise. We need to analyze two solutions with the drivetrain topology. So in the first solution we have just the gearbox and the generator inside the nacelle underwater, and the frequency converter together with the transformer on shore, close to the grid. And then there will be a cable connecting the generator to the frequency converter that can be at different voltage levels, and this is where we need to optimize the system. In the second solution we have all the drivetrain components inside the nacelle and the high voltage cable connecting the turbine to the grid. So the gearbox, the generator, the frequency converter and the transformer are inside the nacelle underwater. So altogether we'll have to present 6 calculations, 6 cost of energy values, 2 of them for the river turbine and 4 of them for the ocean tidal turbine. That's because there are 2 cases of length of the cable for the tidal turbine, because they are at the different distance from the shore. Okay, as we know, tide reverses direction 4 times a day, and water speed is not rated water speed most of the time. It's something between 0 and the rated speed. And from this tidal velocity probability distribution and the energy production, we see that most of energy we get produced at partial loads, not at the rated water speed, but at some water speeds like 50, 60, 70%. So in the task description we have this load profile of the turbine described in a simplified way. We have 4 power levels, 4 load levels: 100%, 75, 50 and 25%, and the time assigned to each of the power levels. So we can see that the rated power the turbine has only for 10% of time. It's not much. So 90% of the time the turbine operates at partial loads. Now to cost of energy calculation. Cost of energy can be calculated as all costs divided by all energy produced. More specifically, costs can be represented by capital expenditures, CapEx, and operational expenditures, OpEx. So CapEx is what we invest upfront, and OpEx is the cost component that describes all the costs during the lifetime of the turbine, like repair, maintenance, and so on. We recommend you make a table in Excel where you represent these cost components, CapEx, OpEx, and energy produced during turbine lifetime. So you can see the 20 years for OPEX and for energy. And at the bottom you see cost of energy. Please note the 400,000 euro per year of OPEX in cell C8. This is the number that varies according to the topology of the drivetrain. So we can imagine that the gearbox with high number of stages will fail more often and will need to repair it. So the costs for high stage number gearbox will be higher than for low stage number gearbox. And this is reflected in the exercise description. You see that for the gearbox with 3 stages, we plan for 400,000 euro OPEX, while for the 2-stage gearbox we plan for 390,000 euro in OPEX. And we recommend actually to try these 2 gearbox variants, maybe skipping the 1-stage topology. Now, in addition to OPEX, we need to enter the data for CAPEX, cell C3, and for the energy produced, cell C12. So let's see how we can find the cost of the drivetrain and the energy. So first we enter the turbine parameters, the rated speed and torque, as well as overspeed, and we can see the system cannot find a good solution for us. So that's because the gear ratio was too low, just 3. As soon as we end it to 8, it gets in place. We also need to put in the right frequency converter type for quadrant, and then almost immediately we find in the report the price of the system and the efficiencies at partial loads. So of course we shouldn't forget the cable. It is not as short as it was. It should be 500 meters for the river turbine, and then we see the efficiencies for the system are extremely low, and this must be because the cable is too thin, and we need to go and change the cross section and check what is the efficiency of the cable now. It is close to 80%, probably not as good as we wanted it, so we can change it again. So overall system efficiencies are now a bit higher than before. So these are the parameters to play: the motor type, the gearbox type, number of stages, and types of the stages. And with the transformer we also can do the changes to the voltage level for the frequency converter and the cable and the generator. And on the frequency converter we can change the types. If we want to see how cost of energy is calculated, we look into cell C14 and we see that it is the ratio where on top we have the sum of C2 and C6, which are the CAPEX and OPEX, and at the bottom we have C10, which is total energy produced by this turbine over the lifetime. So now let's take a look how the power produced by the turbine may look like. So this is for the ocean tidal turbine only, because it works at different velocities of the water, and we represented this into 4 levels. So you can see we have efficiencies at 100% load, 75, 50 and 25% load, and these efficiencies you take from DriveConstructor, from the report, as we've seen before. So here we say we analyze 3 cases, but in fact we'll have to analyze 4 cases for the tidal turbine. So in column G you see there are times. That's how long the turbine operates at certain load, like 100% load it operates 0.1 or 10% of time. So the times in column G altogether make up to 1 or 100%, that's all the time. And in line 8 you see how much power this turbine produces over an average hour. So this what should be used to calculate the power produced over the 20 years of the turbine lifetime. So we first multiply this 509 by number of hours in the day, and then by number of days in the year, and then 20 years. And that's how we get the total produced energy by that turbine in that case. Finally, I would like to remind that there are two solutions to analyze for both the river variant and the ocean variant, with the frequency converter and the transformer inside the nacelle and on the shore. So please don't forget this. And that's all. Thank you for watching and good luck with this exercise.